Let's now define the mole and Avogadro's number. The mole is just a unit. It's a key unit for counting in chemical reactions. We count atoms, we count molecules. Another way we can define the mole is that it is the number that's equal to the number of carbon atoms in exactly 12 grams of pure carbon 12. That's the carbon 12 isotope. Yet another way we can define the mole is quantitatively. 1 mole is equal to 6.022 times 10 to the 23rd. So a mole is just a number, and that number is huge, 6.022 times 10 to the 23rd. This is an inconceivably enormous number. I certainly cannot conceive of the magnitude of this number. This is Avogadro's number. This number was determined to be equal to the number of mole through a lot of measurements, particularly through a technique called mass spectrometry. But this number gives us a really useful way to count up atoms and molecules in chemical reactions and keep track of things stoichiometrically. And thinking of a mole as a number really will simplify your life because 1 mole of anything simply equals 6.022 times 10 to the 23rd units of that thing, whatever that thing is. So 1 mole of pencils would be 6.022 times 10 to the 23rd pencils. 1 mole of people would be 6.022 times 10 to the 23rd people. 1 mole of atoms is 6.022 times 10 to the 23rd atoms. So 1 mole of any substance, doesn't matter what it is, contains Avogadro's number of particles. 1 mole of any substance contains 6.022 times 10 to the 23rd particles of that substance, be they atoms or molecules. And the reason why we use the mole is because matter contains so many particles. Such an inconceivably huge number of particles. It's easier to talk about matter in terms of moles rather than in terms of the individual number of particles. So it just is a simplifying counting unit. So another interesting thing about moles is that a sample of any element with a mass equal to the element's atomic mass is going to contain 1 mole of atoms. So a sample of an element with a mass equal to its atomic mass, that is the atomic mass of that element. And I can even say that the mass is expressed in grams, the SI unit of mass, will contain 1 mole of atoms. So there are 6.022 times 10 to the 23rd atoms in a sample of any element with a mass equal to that element's atomic mass. Okay, that's a lot of words. Let me show you what that means with an example. In exactly 12 grams of carbon, and I'm talking about carbon 12 here, the carbon 12 isotope, there is 1 mole of carbon 12. Another way of saying that is that there are 6.022 times 10 to the 23rd atoms of carbon 12. So the number of atoms, this is kind of conversely, the number of atoms in exactly 12 grams of carbon 12 is going to be equal to the number of atoms in, let's pick another element from the periodic table. Let's go up to the periodic table. Let's just pick phosphorus. Okay, so phosphorus has an atomic mass of about 31. And that means we can say that the number of atoms in 12 grams of phosphorus is going to be equal to the number of atoms in 31 grams of 31 phosphorus. That's going to be equal to the number of atoms in 1 gram of hydrogen. That's going to be equal to the number of atoms in 201 grams of mercury, 201. So we could do this for any element on the periodic table. The sample of that element with a mass equal to the atomic mass in grams contains 1 mole of atoms of that element. So this is a very meaningful definition. If we want to consider how big Avogadro's number is, I can give you a quick example to kind of show that. So to show the sheer magnitude, the magnitude of Avogadro's number, how big that number is. It's very hard to conceive of how big that number is, so we like to develop these little mathematical analogies. Okay, I'm going to give you a little calculation. A sheet of paper is about 0.1 millimeters thick. How far would a stack of Avogadro's number of papers sheets of paper extend in kilometers? We can all kind of imagine a kilometer. So Avogadro's number of sheets of paper, of course, is 6.022 times 10 to the 23rd. Now you can always look up Avogadro's number, but you will end up probably memorizing this number over the course of doing problems in chemistry. So we have Avogadro's number of sheets, and each of those sheets is 1/10 of a millimeter thick. So we have 0.1 millimeters per sheet. I need to now convert that to kilometers. So I have 1,000 millimeters in a meter, and I have 1,000 meters in a kilometer. So this way I can cancel the sheets, I can cancel the millimeters, and I can cancel the meters. And I'm left with 6.022 times 10 to the 16th kilometers. That's how far a stack of Avogadro's number of sheets would extend. Now, to give you some context, the distance to the sun is only 1.5 times 10 to the 8 kilometers. So what we just calculated is 400 times the distance from the Earth to the sun. This 6.022 times 10 to the 16th kilometers. That is an incredible magnitude. So I hope that that little calculation puts kind of into context the sheer magnitude of Avogadro's